Hey everyone, my name is Matt, and in this video we're going to be using pandas to analyze some data and find out, has The Simpsons gotten worse over time? So you can think of this as exploratory data analysis. So we'll be doing some high-level statistics, we'll be creating some lovely visuals, and we'll just be progressing through the data set to try and pull out some stories or insights. So this is going to be a bit of a walkthrough, a bit of a showcase, but the key takeaway from this should be, where could you start when doing exploratory data analysis, and how do your questions evolve and develop as you get deeper into the data set? How could you represent and frame and contextualize data visually to tell a story or lend itself to a narrative? And most importantly, how do you take these principles and apply them to data sets that you'll analyze in the future? So before we get into it, here's what we'll be doing and what libraries you'll need. So firstly, we'll be using pandas and NumPy to get the data in a format that we can properly analyze and manipulate. And secondly, we'll be using Matplotlib, Seaborn, and a tiny bit of Plotly to actually visualize the data. And really that's it. So without further ado, let's just get into it. Okay, great. So what we're looking at right now is just my Jupyter notebook, and you can see we already have some headings just to guide us, and also there's a bit of code here. So this code is actually from the previous video where we were looking at how do you scrape IMDb for review information. So we picked The Simpsons, we scraped all the Simpsons information, and then we put it into this lovely data frame here. If you're just interested in exploratory data analysis, don't worry, you don't have to copy this code. I'll actually save its export as a CSV document that you can read, and I will put a link to it from Kaggle in the description below, so don't worry. But if we call this data frame object, here's what we're going to be dealing with today. So we have our season number, the episode number, the episode name, episode air date, episode score, episode votes, and episode description. We won't be using all these columns necessarily. We're mostly interested in episode score since we're trying to figure out, has The Simpsons gotten worse over time? So yeah, we'll be using score, possibly air date, well definitely air date, and definitely episode number as well. So before we get into any actual statistics, let's find out a bit more about this data frame, or rather this data set. So if we do df.info, and df is the data set we're working with, we see here that, okay, we've got the columns, we have the counts, and we have the data type. So the counts look great. We can see we have 705 rows, and we have 705 of every column, so we have a complete data set. Got the names, episode numbers an integer, season numbers an integer, episode numbers an integer, episode name's an object, that's fine. Episode air date's an object. So that is going to definitely throw up some problems in the future. This should be a datetime object. Episode score is also an object. We can see here, though, it's clearly a float, so we'll need to change that. Episode votes is also an object, where that should be an integer. We might not use episode votes, but I think it's still worth fixing. And episode description is an object. We can see it's just a string, so that's totally cool. So first things first, let's fix these data types. The way I like to do these is I'll tell you what I'm going to do, I'll speed through the actual coding process, and then I will come back and talk through what I've written. So let's fix these data types. Okay, cool. So we've now fixed those data types. We can see here that air date is now a datetime object, score is now a float, and episode votes is now an integer. So how did we do that? So datetime, simply we called the datetime, we called the air date column. We then used the pandas library and then the toDatetime function, and then fed into it that air date column, and that converted it successfully, which is great. Just a caveat, if you do have incomplete information or inconsistent information, this might throw up some errors. Datetime can be a bit finicky to work with, but just be wary. And for these two, so episode score, what we did was we called the column and we used the asType function, and then we fed into it the float argument. And what that did is it converted all the input of that, or rather all the values in episode score, into a float. Similarly for episode votes, we converted it into integer using the exact same method, but saying integer instead of float. So super, we now have a data set that we can work with. So let's start answering the question, has The Simpsons gotten worse over time? Let's start off with some high-level descriptive stats, some basic stuff. So what we can do is say df dot episode score, because episode score is our dependent variable. We're interested in finding out what's happened to it. So let's call the mean. Cool. So on average, across all 32 seasons, the episode score mean is 7.2. That's pretty high considering, I'm not sure what most series on IMDb are, but 7's a good score. But it doesn't answer our question, has it gotten worse over time? So really what we should do is we should group this by the season number and then apply the mean function to it and see what happens. So let's do that. So group by season number. Great, and now we have the season number along this column here and then the episode number, and immediately we can see a trend. And just to make that a bit more obvious actually, let's round this to 1 decimal place. So we can see season 1 is 7.8, very high, close to the overall mean actually, and it increases to 8, as far as 8.4, and then it looks like it just steadily decreases actually over time, quite linearly. So that's really interesting. Let's look at another thing. Let's look at how about the min? How about the worst episodes of every season? So the worst episode of season 1 is 7.4. That's really high. That's actually about the mean. And we can see that it decreases. Actually, sorry, it increases initially. Actually, it fluctuates a bit, doesn't it? It fluctuates from 7 to 5 to 7 to 5 to 6. So that's a bit messy. How about standard deviation? So we can see season 1 has variable standard deviation. That's cool, but we don't want to go through like every function really and then eyeball it this way. I'd like to see everything all at once. So fortunately for us, Pandas has a mega function called describe to put all these descriptive stats in one place. So instead of standard deviation, let's call describe. Excellent, and now you can see you have your count, mean, standard deviation, min, max, and then your quartiles. Excellent. And just from looking at the count, we can see there's a bit of so season 1 actually only has 13 episodes. Season 2, 22, 24, 22. So there's some variability there. That's really interesting. Standard deviation, yeah, you can see some fluctuations. Min, max, quartiles we're not interested in. So I'm actually keen on dropping the quartiles. So let's do that very quickly. Cool. And what we're gonna do now actually is plot some of these on a graph. Looking at the numbers is fine, but I'm more of a visual person, and I think it conveys information in a different way. So let's plot these on a Scatterplot. First, let's, I'm going to code this actually, and I'll be back in a sec. Okay, cool. So this is really interesting. First, what we did was we assigned that thing we did earlier into an object called description data frame. Then we took our description data frame and we actually reset the index because the season number was the index column, and that isn't necessarily the easiest thing to call. So we reset the index and that just gave it a new index and shifted season number to its own column. And then we actually converted the columns into a list, so we can just cycle and iterate through it using this for loop. So we called Seaborn, Scatterplot. The data is the descriptive df, descriptive data frame. The x-axis is season number, and the y-axis is whatever we want. So actually, it says count at the minute, so we can see we got some pretty interesting graphs, but I actually made a mistake here. We should change this to call. So now we get some pretty interesting outputs here, which is cool. So season number, as you would expect, it just goes up. So it's just a diagonal line. But episode count by season, ooh, yeah. So we can see that season 1 actually has 13 episodes before jumping up to 22 in season 2, which is really interesting. And then it stays relatively stable throughout. If we look at the mean of the scores, then we can see that it does in fact go up, and it has quite a dramatic dip over time, and it seems like it is constantly going down, which is interesting. Just be aware that this doesn't start at 0, it starts at 6.5, so this might be an exaggerated drop, but it's still relatively significant by the looks. And in terms of standard deviation, so this is the variability in season scores, or rather in episode scores within that season. So we can see that episode 1 is pretty consistently whatever its mean score is. And then there's some variability, and then it becomes more variable, a bit more volatile, but it's quite difficult to see, to be honest, in this visualization. In terms of min, so before it was quite difficult to see at just the numbers, but when you plot it, you can see that the minimum score, so the worst episode in that season, tends to trend downwards, it looks like. And the best episode in every season also looks like it trends downwards. So that's, already we have some really cool insights. The issue is though, this is pretty low resolution. It tells you a story, but it really kind of omits the nuance and depth of this story. So there are better ways of visualizing this, you know. So let's start off with actually a heat map. Let's see what that looks like when we represent the episode number and season number and then the score. See what happens to the score as a heat map. So first thing we need to do was actually pivot it. So we took our data frame, we called our data frame, we called the pivot function, and then we said we want our x-axis to be the season number, we want our y-axis to be the episode number, and we want the values that correspond with each other to be the episode score, and we get this lovely visual here. But this is not a heat map, it's just a data frame. So let's call Seaborn now and turn this into a heat map and see what it looks like. Cool, and we are back. So this is really neat. I really love the way this turned out. So what we did is we have our pivoted table. We just set the size of the figure to 1616 to get a lovely square. And then we called Seaborn Heat Map, gave it the data frame, turned on our annotation so we get the numbers, changed the heat map color scheme to this one here, and we removed the color bar. Since we have our annotations, it's a bit redundant. And if we look at it in its entirety, we got this really beautiful image that does suggest, hey, the episode scores are going down. This is one insight, but the other insight is you have these anomalies every now and then. So you can see in episode 9, one of the episodes was pretty weak and it got a score of 5. Whereas also later in the later seasons, you can see that there are some instances of top quality episodes. Sometimes they do actually beat the earlier seasons too. So 8.5, 8.3, 8.2. And it really just builds up this beautiful image. It represents that, yeah, the average score, the score of every episode by season, is declining. So more ammunition to suggest that, yeah, things are getting worse. But let's represent it in a different way. Let's try using a scatter plot with our x-axis as time and our y-axis as score and see what happens. Okay, cool. So when you plot this on a scatter plot, we get this really lovely visual here. So we have episode air day along the bottom, episode score along the y-axis, and we can get this lovely shape that again suggests, the earlier seasons, they kind of went up, peaked, and has been a slow decrease ever since. So this is the base scatter plot we'll be using for this analysis, but there are things we can add on top of it to actually better contextualize the data. So I think actually first, just for fun, I guess, let's see when seasons start and end. Let's draw some lines on top and label them just to give us an idea of how long seasons necessarily last with The Simpsons. So I'm gonna copy this down here, and let's have a go at adding some lines to represent the season start times. Okay, so the code for this is a bit convoluted, but I'll try my best to talk through it. So basically what we did was we got a series of season start dates. And the way we did that was we called df, we grouped it by season number, we got the episode air date, and we wanted the lowest episode air date in every season. So we could assume that's when the season started. And then we turned that into a list object. And the reason we did that is because we wanted to iterate through it. So what we did was we have our we have a for loop here. So for season start in season start date. What we did was we plotted a vertical line with the season start as the x coordinate. And then these things are just formatting, right? So that's how we got these lines. To get these text, what we needed was what we needed was also an x coordinate, but we also needed a season number. So what we did was we wrapped the season start dates list in this enumerate function, and basically what that does is it gives us the iterative of that list. So we would get the season dates, but it would also give us an index for that iterative value. So season, so it would start at 0 and then work all its way up to 31. And basically what we did was, so we said, okay, so the x coordinate for the text, let's give it the season start value. For the y coordinate, make it 9.8. So that's just where it sits on this y-axis here. So 9.8. And then what text do we want? We want the text to be, and this is just a format string, s, and then the season number. So actually it starts at 0, which is not true. So it really should be s plus 1. And if we just run this again, we can see, okay, season 1, season 2, season 3. So from this graph, what we get is that, yeah, the Simpsons are pretty consistent with their release schedule, it seems. At least until season 1 was really quick. Season 2 then started shortly after. They remained consistent. And then season 23 looks like it was slightly longer. Season 25 and 26. Season 25 seemed like it was really short-lived. And that's quite interesting and maybe worth delving into in the future. But this is neat, just to give an idea of how the episode scores are distributed by season. So we can see that, yep, it rises to about season 8. And then that's when we start to see a decline. And you can see that within the season 9 kind of area, it is decreasing. Cool. So that's really nice. That's a really beautiful graph. Let's start contextualizing this data in a different way. Let's apply a mean line. So remember we looked at the mean of all seasons? Well, let's actually plot that line and see where episodes fall in between them. So as before, we're going to copy some text, or rather we're going to copy the code we wrote earlier. And just give me 1 sec. Okay, great. So that was a lot more straightforward. Basically, and actually I'm just gonna correct this quickly while I talk. So basically what we did, we have our base plot as before. And what we did is we assigned the mean of episode score throughout all the episodes across all seasons to this mean variable, and we rounded it to 1 decimal place. Cool. And then we said, okay, on the plot, calling PLT, give me a horizontal line. So XH line gives us a horizontal line to plot along the y-axis. The y coordinate is the mean, which we declared earlier. The label is mean, and then brackets, and then the mean value. And basically when you call this label function, it means that you can call legend later on, and it will actually give you a legend. So if somebody were to pick up this graph later on, they know that this red line is the mean. So that's excellent. And then actually something I didn't explain earlier is you can format these lines. So LS stands for line style, and you can give it these colons, or you can give it 2 dashed lines and you get a different aesthetic, which is cool. C means color, and you can give it red or green or gray, whatever you'd like. And LW is line width, so you can give it any number you'd like, and obviously it impacts the thickness of it. Then we call it legend, and the grid lines are exactly the same as they were before. So this is excellent, and this paints a really lovely picture where we can see that, before, at about the year 2000 is when things started getting pretty variable. So we can apply the season start dates on top of this if we want, but it might get a bit noisy. So I'm just going to eyeball it for now. But we can see that in the earlier seasons, there was a rise, very much above what the current mean is. And then at around the year 2000 is when things started to become more variable. And then 2004 onwards, it looks like the majority of episodes actually fall beneath the mean, which is really interesting because it kind of implies that the earlier seasons of Simpsons keeps its score afloat, which is really interesting. That's a really lovely insight from this. Another thing we could look at, we can already kind of tell from just looking at the scatter point shape that there's a rise, then there's a decrease. But what would be really cool is to apply a line of regression or a line of best fit to actually measure, okay, what does that decrease, what does the decrease look like? How steep is the line? But also, how much is the quality of The Simpsons decreasing per episode? So let's do that next. Let's apply a line of regression. Okay, I ran into a slight bug, but I'll explain in just a moment. So basically, we get this lovely line, but I'll talk about it in just a sec. So what we needed to change was the x-axis. And the reason is because it gets a bit difficult when you're plotting date time along the x-axis. I won't get into the reasons here, but basically it messes up the formulas. You have to convert it into a different format and then reconvert it back to change the labeling, and it just gets messy and it messes up the regression formula. So instead what we did was we actually created a new column called episode number abs, which is just absolute. So this disregards the seasons as a barrier and just basically counts. It's basically the index. And we said episode number abs equals range, which is the length of the data frame. So it goes from 0, when it really should be 1, to 702, if I remember. So actually, I'm just going to fix that now. There. And then we used that as our x-axis instead. Cool. The formula to get a line of regression, we actually use numpy. So firstly, we defined our x and y. So x is the episode number absolute, y is the episode score, and then our m and c. So this is interesting. If you think back to grade school, you'll remember y equals mx plus c, which is the formula to actually plot a line of regression. So m is the gradient or the slope, so how steep the actual line is. And then c is the y-intercept, so that's where it intersects on the y-axis when x equals 0. So what mc is numpy, polyfit, your x variable, your y variable, and then 1. At the moment, I can't remember what 1 is, but just don't forget that. Put in 1. So what we then did is we rounded it. So we rounded your m value, and we rounded your c value to 5 decimal places. And the error I was getting initially was I was rounding it to 0 decimal places, which made it equal 0, because it's a very, very small number. So be careful with that. I rounded it to make it just a bit easier to read. And then we have our formula here. So it's a format string, y equals m, the gradient, times x plus c, the y-intercept. And the reason we did that, the reason we wrote it out at all, is to apply to the label, so we can add a legend to our graph. And then we just plotted the line. So plt.plot along the x-axis, put the x value. Along the y-axis, we have our y equals mx plus c formula. And then we have some line formatting. We discussed this earlier, so I won't get into it. And then our label for the legend is the formula itself. And when we plot this, we get this really lovely regression line of best fit plot in red, and it clearly shows that there is a pretty gradual decline in episode score over time. And how much is that? Well, we can see that per episode you're losing about 0.003 stars. Really small, but it kind of shows that this is a slow burn, a slow descent in quality. It'd be really interesting to see what happens when we hit season 60. Will this line of regression still hold up? Or will the quality suddenly start to increase again and we'll get some kind of rebound? Really neat and really cool to actually put a score against it. How about the quality of episodes per season? What does that look like? Okay, so we can actually use a Boxplot to look at the distribution or the variance in episodes per season, because I'm interested in seeing how that may be varied over time. So let's code that up. Okay, great. So that was a lot more straightforward. It's literally one line, more or less, and then we changed the fig size and added a grid. So what we did is we called Seaborn. We called the Boxplot function. We fed it the data frame, and we said, okay, make X the season number and make Y the episode score. And what we get is this really lovely curve. So for those unfamiliar with boxplots, basically what they represent is the distribution of data. So the whiskers, the endpoints of the whiskers represent the maximum and minimum values within a distribution. The middle line is the median, and then the ends of the box represent the interquartile range. So your 75th and 25th percentile. And this represents the distribution. And what these diamonds represent is, I believe, if the value is greater than 1.5 or 2.5 of the standard deviation of that distribution. So basically it means it's an outlier. It just means that it's so far out of the normal standard deviation that it could be considered anomalous. It could be considered an outlier. So what we can see is in season 1, a lot of the episodes are actually quite closely contained. They are all so close to each other that we can't even see the whiskers. And then everything that falls out of that interquartile range is basically considered an outlier. So that's just, it's a really tight season. They are consistently about 7.8. And then season 2 has a bit more of a distribution, but you can see the median is quite high. Likewise, you can see the median increases and increases and increases. Season 8 seems to have the highest ever episode, the highest scored episode, which is really interesting. And then you get a decrease. What you can glean from this, we already know it decreases, but what you can glean is that season 13 looks like it was actually a pretty tight season too. It was consistently above 7. With quite a few outliers, whereas season 23 looked notably not so great. It had huge variability in its episode qualities, and it actually also features the lowest rated episode ever. So season 23 seems like a pretty contentious one. And we could delve deeper into this graph, but I'm going to move on to our final plot. And what that is what was the worst and best episode per season. So what we can do is actually use a library called Plotly. I don't necessarily like using Plotly because I prefer to work on a lower level when I plot my graphs, but for things like this where we just kind of want to interact and explore the data on the same graph, really, it's very convenient. So I'm going to code this up very quickly using Plotly, and yeah, let's check it out. Okay, cool. So what we have here is a really lovely interactive plotly graph. So you can actually hover over these points and we'll give you a bit more information. So we can see here that these two seem to be the highest, and what we have is you only move twice at season 8, got 9.3, very cool. Whereas Homer's Enemy on season 8 as well actually got 9.3, so season 8 seems to be a really strong season. Whereas if we look down here at the worst rated episode out of our entire data set, we have Lisa Goes Gaga. Weird, I don't actually know that much about that episode, but we can see it's again on season 23, which was the most contentious season, according to the Boxplots, and it actually got 3.9, which is shocking. We can make this even clearer, actually, if we change the x-axis from episode air date to season number. And now we get an even clearer picture of what is the worst and best episode per season. So we can see here for season 6, which was actually that, I think earlier in the heat map, this was the anomalous one. Oh no, this was the anomalous one. So this is in season 9, all singing, all dancing. I don't remember that one. I do remember the clip show though, because I think this is the one where they rehashed a ton of episode clips. It was just really boring to watch, so no wonder it got quite a low score. But awesome. So there you have it. That's our analysis of our Simpsons dataset. I think we've pulled out some really interesting insights and in the process created some pretty beautiful visualizations. So I've just hidden all the code cells and let's just do a victory lap of all the things we've created. And yeah, wow. We have a pretty compelling set of visuals and statistics to definitively say, yes, The Simpsons has, in fact, gotten worse over time. That is truly a shame. But there you have it. So if you did stick around to the very end, thank you very much for putting up with that. It is very difficult to do these kind of videos in one take, so I can appreciate there were some stuttering and misspeaks in parts, so apologies for that. But again, thank you for your patience. The code for this video will be in the Kaggle notebook that I'll link in the description below. And also the dataset for this activity will also be in that same Kaggle notebook. So if you want to follow along with me, or if you want to do your own data analysis, please do feel free to download it and share what you come up with. I'd love to love to see how else you could analyze this data. And there we have it. Again, thank you so much for checking out my video. I really appreciate your time, and I hope it was helpful to you. Brilliant. Hope to see you in the next one. Take care.